Hello and welcome to this video on complex numbers. In this video, I'll briefly discuss what a complex number is, why we might use complex numbers, and then I'll end by showing you the different forms that you might see a complex number expressed as. So let's begin by explaining what a complex number is. A complex number is made up of two parts. It has a real part, which is just a normal number, and an imaginary part. Now, the imaginary part is literally a real number, it's just been times by the root of -1. You might also see root of -1 expressed as maybe I, or sometimes it's expressed as Z, and less common, but sometimes you might see it as J. Commonly what you might see is Z squared being expressed as -1, or Z might be expressed as plus or minus I. Why do we use complex numbers? Complex numbers are useful as they can be used to represent two real independent variables with the same dimension. A good example of when to use a complex number is when you think of circuits, and in particular an AC circuit. A single frequency circuit has both amplitude and a phase shift. So complex numbers might allow you to denote the phase shift between, say, the voltage and the current, which if you use normal scalar numbers is a little bit difficult to do. So complex numbers allow you to express that. The different forms of complex numbers. Much like when picking a coordinate system to choose from, say Cartesian or polar, different physical situations might require it to express the number in a certain format. This video is going to look at the main three, and those are the rectangular form, the polar form, and the complex exponential form. The rectangular form. The rectangular form of a complex number is expressed as a, the real part, plus I, b, which is the imaginary part. Sometimes you might see the I as a j, but most of the time in this video I'll be using the I. If I draw an axis where the real part is on the x-axis and the y is the imaginary axis, so they're perpendicular, we can easily see where this form comes from. So if I have a point here and draw a line from the origin to that point, then if we were to use vectors, we would go along the x-axis or the real axis, and then we would go up the y-axis, which is the imaginary axis, and that ends up with the real part, A, plus the imaginary part, IB. Now we know what the form looks like, let's look into how to add, subtract, multiply, and divide these types of numbers. On the top of the screen, I've written out two different complex numbers that I'll be using as examples for this next part of the video. Using these two numbers at the top, add A1 and A2. I'm going to write them out in full. All of the real parts need to be added together, and separately the imaginary parts need to be added together. So adding the real parts, 2 plus 7, and then adding the imaginary parts, so put I outside the bracket, 3 minus 6. Altogether, and the process is exactly the same for subtraction. Subtract the real parts. Be careful, this should always be a plus. but then subtract the imaginary parts. Now I'll show you how to multiply these numbers. Multiplying complex numbers is just like normal multiplication of any brackets. However, you do have to remember that there are imaginary terms here and that I squared is equal to minus 1. So if you multiply two imaginary numbers together, it ends up being real. And as we saw in the subtraction and the addition part, all of the real terms are grouped together and all of the imaginary terms are grouped together. So let's start with the real terms. So 2 times 7 would be a real term. And the next real term that we get will be if we multiply both of the imaginary terms together. So 3 times 6, 18. It's minus 6, so it's minus 18. But then we also have I times I, which is minus 1, which turns the minus 18 into a plus 18. So do be very careful when it comes to your signs because it can be a little bit tricky sometimes. Now the imaginary part. 3 times 7, 21. And then 2 times minus 6, it's minus 12. If we simplify this out, again, I will just reiterate the importance of being careful with your signs here, because remember that I squared is minus 1. It's not 1, but minus 1. So do be careful, and if it helps, maybe write out every single step. Moving on to division. Division using complex numbers is slightly difficult because we've got an imaginary number on the denominator as well. So what we usually do to get rid of this is times the top and bottom by the complex conjugate. So a side note, the complex conjugate is usually denoted by an asterisk. All it does, it keeps the real part the same. However, it changes the sign of the imaginary part. So that's what the complex conjugate of A1 would look like. And just to show you for A2, so just switch the sign of the imaginary part. So we've got our division here, A2 divided by A1, times both the top and bottom by the complex conjugate. Essentially, what you're doing is timesing it by 1. Top and bottom here will just cancel out. So you're not changing the actual division. Now multiply both top and bottom. So they cancel out. So that's how you divide complex numbers in the rectangular form. Just to reiterate, times the top and bottom by the complex conjugate of the denominator. This will get rid of the imaginary term in the denominator. Multiply it out, simplify it, and that's how you divide rectangular form complex numbers. We'll now move on to the polar form of complex numbers. The polar form of complex numbers. Much like we can use Cartesian or polar coordinates to make a problem easier, we can also express a complex number in a polar form should we need to use a polar coordinate system. I have done a video on polar coordinates in 2D if you should want to have a look at that. Again, if I draw an axis, we can see where this form comes from. Here is my axis. Exactly like for the rectangular form, we've got the real axis, which is the x-axis, and the imaginary axis, which is the y-axis. Again, if I draw a point and a line to that point, for the rectangular form, we use vectors to describe this line. However, in the polar form, we will use a magnitude, r, which is the length of this line, and an angle from the x-axis. And this is exactly what we see in the polar form. You have the r, the magnitude, or the length of the line, and theta, the angle from the x-axis. From a previous video, we derived how to go between the coordinates of a Cartesian and a polar system. I've included these in the video as these relations will be very useful when it comes to manipulating complex numbers in their polar form. I'll now go through how you multiply and divide complex numbers in their polar form. Multiplication. Timesing and dividing using complex polar form is actually easier than the rectangular form. For example, a1 times a2, so writing that out in full. In order to actually do this, we times the magnitudes, so 5 times 2 in this case is 10. Since it's angles, we want to add them. And it's a very similar process for division. So divide the magnitude, so 5 divided by 2. I'll just keep it in its fraction form. Instead of adding the angles, since it's division, we want to subtract the angles. So 25 degrees minus 20 degrees will leave us with 5 degrees. It's pretty much easier to multiply or divide a complex number in its polar form than in its rectangular form. When it comes to addition and subtraction, it's a little bit more tricky in the polar form. In order to add or subtract a complex number in its polar form, you first need to convert it into a rectangular form. So to do this, we use these relations, which I've included and left on the left-hand side of the screen. Again, for a derivation, please do see my video on polar coordinates in 2 dimensions. The best way I can show you of how to approach this is with an example, so that's exactly what I'll do. I'll do an example to show you the best way to approach addition and subtraction for a complex number in its polar form. As I mentioned before, the way forward is to convert these polar forms into a rectangular form. If we remember, the rectangular form has the real part, which going back to the axes is from the x-axis, and an imaginary part, which is a number times by I, on the y-axis. So each complex number will have an imaginary and a real component. Therefore, if we're adding 2 of these together, we need to add the real parts, and then we need to add the imaginary parts. To find the real parts and add them together, we use these formulas here, the x and the y. Again, if you do want to see where these come from, I do recommend my video on polar coordinates in 2 dimensions. So in order to get the real parts of our polar forms, we need to times the r values, which is the numbers in front of the angles, times that by cos theta, and that will give us the real parts of the polar forms. So let's do that now. So the first term will be 2 cos 45 degrees plus, as we are adding, 8 cos 30 degrees. We've got the real part, now we need to add the imaginary parts. Just like we did for the real parts, the imaginary parts we get from the y-axis. So here, y is r sine theta. So to add the imaginary parts of our example, include I, it would be 2 sine 45 plus, as it's an addition, 8 sine 30. If we type all this into our calculators, we'll get our answer in a rectangular form. We can convert this back into polar form should we need to, and to do that, we will use the inverse functions, which is r theta here. So I'll do this in a different colour. To get r, or the magnitude, we need to use the square root of x squared plus y squared. Now in the rectangular form, x is the real number, the first value here, and y is the number within the imaginary part. So to get the magnitude, r, we would use the square root of 8.342 squared plus 2.414 squared. And that will give us an answer of 8.684. To get the angle, we use the inverse tan. So y is the number within the imaginary part. In this example is 2.414. And x is the real term. So altogether, in polar form, and again, the process is exactly the same for subtraction. Just remember that instead of adding terms, you would minus the terms. I'm now going to move to the last form of complex numbers, which is the complex exponential form. The complex exponential form is self-evident from its name. It's just expressed in an exponential form, where the imaginary part is in its indices. Because of this, algebraically, complex exponential form works the same way as polar form when you multiply or divide. So for the coefficients, if you were multiplying, you would times the coefficients, but you would add the angles, and if you were to divide, you would divide the coefficients and minus the angles. This form isn't really used often, but it is useful when deriving formulas, and it is the basis for some methods of circuit analysis, and it can be related to the polar form and the rectangular form using this relation. That's all I'm really going to say about the complex exponential form. It's not a form that I've really used frequently. However, if you would like a little bit more on it, I can do another video just on this form, just to get used to manipulating it and maybe converting between the different types of forms. But for today, I'll leave it here. If you'd like a few more worked examples, do comment below and I'll try my best. If you found this video helpful, please like and subscribe or tell a friend. And thank you for watching. Have a nice day.